Hello, my name is Fausto Gonzalez, and this is the thesis that we did in August 2007 between my classmate Francisco Alvarez and myself, Fausto Gonzalez, for obtaining our university degree as electrical engineers for La Universidad de Carabobo, or University of Carabobo in Venezuela, and for which we obtained the higher score, 20 out of 20, and received an honorific mention. The name of the thesis is Editor Ladder PLC UC, or Ladder Editor PLC UC. UC, or UC in English, stands for Universidad de Carabobo, or University of Carabobo, as I mentioned before. It was made using Java 6, and it is a compiler from PLC ladder programming language to microcontroller assembler. The purpose of this thesis was to compile from ladder programming language to the assembler language and then to the binary code of a mid-range core microcontroller PIC16F877 made by the company Microchip Technology, because about a year before that we did our thesis, two other students from our same university did a prototype of PLC that they call PLCUC, which used the mentioned PIC16F877 at its core, with the idea of producing this prototype of PLC to use it in our university automation lab for teaching other students how a PLC works and how it can be programmed. But because there was not a compiler from ladder to the microcontroller assembler, the only way to program that PLC-UC was using assembler or a high-level programming language like BASIC that could compile into the instruction set or binary code for that microcontroller for being able to program it. For the students in this automation lab course, learning a high-level programming language or an assembler language was beyond the main idea of teaching them how to program in ladder. Ladder is one of the most used programming languages among PLCs, even though the ladder programming language is not completely standardized between different PLC brands. In general, there is a similarity across various brands of PLCs, and understanding how to utilize it is very crucial for anyone interested in this PLC field. So, to solve this issue, we did a compiler that the end user would use ladder for programming the PLC, and after compiling, the software would transform this code into assembler code and then into hexadecimal code for being able to program this PIC16F877 microcontroller. To do so, we use Java for programming the user interface because Java is multi-platform, meaning that the same compiled software can run on different platforms and operating systems that have an implementation of the Java virtual machine, like Microsoft Windows, Apple macOS, Linux, Oracle Solaris, and many more, without the need of recompiling the same software for each operating system. In consequence, the Java compiled code is portable, which is one of the biggest advantages of this programming language. Talking about the PLC and the PLC ladder software for this prototype, it has 20 digital I/O ports, of which 12 are digital inputs and 8 are digital outputs. We define in our software that there would be up to 64 internal memory bits, 8 timers, and 8 counters as well. For making the programs that then would need to be transferred to the PLC-UC, the end user can use normally open here and normally closed contacts for detecting rising edge and falling edge detection, as well as XOR, not XOR, or the negation of the XOR for rising edge and the XOR for the falling edge detection as well. For the coils, there are normally open and normally closed coils, as well as a set and a reset coil. Talking about the timer blocks, as I mentioned already, there are up to 8 timers that could be inserted into the program. Each timer can be configured as a T on or time on delay, or as a T off or time of delay. Also needs to be configured the time base between 2 milliseconds, 10 milliseconds, 1 second, and 1 minute, and finally the preset value, the preselection value. That is an integer number between 1 and 9999. Let's say here that we put 2, enter, and here we select minute. Save, yes. Each timer doesn't matter if it's time on delay or time of delay, they have one input and one output. And finally, talking about the counter blocks, as I also mentioned already, there are up to 8 counter blocks. Each counter can count from 0 up to 9999 cyclically in integer steps of 1. Each counter has 4 inputs: R for reset, S for set, CU for count up, and CD for count down. They also have 3 exits: E for empty, that is activated when the count goes down from 0 to 9999 after having the CD or countdown input condition activated. D for done, that is activated when the count match the preselection value. And finally, the F for full, that is activated when the count goes up from 9999 to 0 after having the CU or count up input condition activated. For changing the preselection as well as in the timer blocks, we just need to do double click on it. And here we change the preselection to whatever value that we want. Let's say 15. Enter and save it. Yes. And here we can see that it was changed. Okay, well, now to finalize, I'm gonna do a small example for you guys to see how everything works. I'm not gonna go over the details of the design that goes beyond the intention of this video, but I just want to show you how to use this software, this piece of software. So right now, as I was doing before, I did a new circuit and I inserted a new circuit here for when each time when I insert a new circuit, there is a grid here. I can even show or hide the grid here. The grid has 8 rows and 11 columns. Here is where I can put all the circuits or all the elements for completing each circuit. So I'm gonna start. I can first do all the elements. I do here the connections. Here, I put this one here. And right now, I'm gonna give the references or the names for each one of these elements here. Here, percentage I0, percentage I1, from I0 up to I11, they would represent the inputs, the input, the PLC input, digital input. it is necessary to put the percentage at the beginning to let the PLC know that these are internal variables for the inputs, and for the output would be percentage Q. I verify the circuit, I insert one more. So right now I'm gonna do this one here, this one here, and I'm gonna insert a timer. This one would be percentage and 0. Timer 1 dot Q, and this one double click here. In seconds, I'm gonna do it in minutes. The time base in minutes is a T-on, it's already selected, it's the default. I'm gonna do it 2, so 2 minutes, enter. Yes. I verify it. Now I do one more. Again, I normally open contact and a timer. The timer would be timer 1, it's a T-on. This one is in second, and I'm gonna put 90 seconds. Yes. So this one is 2 minutes. The timer 0 is 2 minutes, and the timer 1 is 1.5 minutes or 90 seconds. And this one, the reference for this one would be timer 0 dot Q, or the exit for the timer 0. Now another circuit. And the counter. This one would be I1 counter 0 exit D. This one, when it's done, this one would be percentage Q0. So I just need here to connect. This one would be connected to the up. This one would be connected to the reset. And this one, if I connect it like this, would be like an OR between these two conditions to do a reset. And I want it to count up to 5. Enter, save it, yes. So counter 0, it counts up to 5. And the last circuit I selected here, and I do it here, would be normally open circuit, normally close a contact, sorry, normally open contact, normally close contact, and it goes to a coil. So here percent M0 M0 dot Q, the exit of timer 0, this one, is the reference, and this one would be the exit, physical exit for the PLC, exit 0 for the PLC. Okay, now I finish. One more thing I would like to show is the alias. It is not necessarily to do the alias, but it's a good practice sometimes to do it, because it gives like an abstraction of not needing to remember all these variables. We just put like a name for each one of these, and it's easier sometimes to understand the design that we do. So let's put I0, I want to call it a star. Enter, save it. I1, let's call it a stop. Enter, save it. M0, these are the internal memory bits here. I want to call it wrong condition. And lastly, the Q0, I want to call it, the exit would be like a light. So if I press here, this one, I would be able to see it a little bit easier, these conditions here. This is the wrong condition. When these conditions occur, this one is set. When this condition wrong is set, and okay, here continues. The stop, the counter resets on the stop condition. Is easier like that to remember. And the light is activated, would be activated when the wrong condition is on, that is here, and the timer 0 hasn't counted the 2 minutes, hasn't finished counting the 2 minutes. I can put it again the original way. And right now, the only thing I will need to do is save the design. Let's put it here in this sample 1.plc. This is the extension that we put it. And the last thing would be translate, do the translation. And as we can see, this one utilizes 13% of the internal memory for the microcontroller. This thesis is also, with this thesis we could also do the programming for the PLC, but because I don't have it right now connected to the computer, I cannot physically do it. I hope that you guys enjoyed the video, and anything, please leave it in the comments. Bye, thanks.